Well, let me recall what happened in the previous lecture. And we'll try to explain in more details. To calculate the group cohomology, yes, the second group homology of G coefficients in A, we can use bar resolution, and particularly for the second homology, we need this part of resolution. And we need to take the homology of this complex here, and the elements that go to 0 are denoted by Z2 or GA, and the elements that come from there are denoted by B2 GA. And this lies in this, and we have projection to like H2 is the factor group. So by definition, bar n is simply Zg tensor n times tensor over z Zg. So hom over G is the same thing as hom of the Zg. Hom over G from bar n to A is isomorphic using the adjunction isomorphism to hom over z from Zg tensor n to A. Yes. So this is a free Z module. With the basis G1 tensor Gn for G1 Gn from G. Yes. So in fact, it is isomorphic to it's isomorphic to hom in sets from G in the nth power to A. Yes. Here it is an abelian group, yes, with respect to pointwise sum and multiplication by element from Z. And well, in in this terms we have this part of bar resolution, not bar resolution, the complex that we obtain after applying home G.
Can you explain the last isomorphism?
What?
Can you explain the last isomorphism?
Well, this is basis.
Mm-hmm.
It is parameterized by n tuples in G. And if you have a basis, then a map over Z is the same thing as a map of sets from basis to there. The values of that linear function are uniquely determined by the evolution of the basis. So we have home in sets from G times G to A, then here from home sets from G to A, and here home sets from G to the third power to A. Yes, and so now what is differential? Where it sends some function G, not G, the H from G to A. Well, if you apply all our definitions, we have defined the differential in bar resolution. The previous lecture I explained how it can be applied to this in these terms. So H goes to a function delta H. Yes, where delta H of G1, G2 is what is sorry. It is H of G2, I think. Sorry. Three terms has to be. Yes. So it is H of G2 plus minus H of G1, G2 plus H of G1 times G2. Yes. And if you have some map F from G times G to A, then it goes to the map delta F, where delta F of G1, G2, G3 is simply F of G2, G3 minus F of G1, G2, G3 plus F of G1, G2, G3 minus F of G1, G2 times G3. Okay. So now we started to consider the problem of description of extensions. So we take an extension E G of G by an abelian group A. And such an extension defines a G-module structure on A. So extension determines G-module structure on A, and we fix the structure. and want to describe all extensions inducing the structure modular isomorphisms of extensions. What is isomorphism of extensions? I have said in the previous lecture. It is like a map that makes everything commute, and on the left and on the right it is identity map. So what was our algorithm? Our algorithm was to take some set theoretical map sigma from G to E such that it was alpha and beta, yes? Such that beta sigma is identity on G. And if sigma is a group homomorphism, then we will get a semi-direct product. But if not, then we have to lead in some way with this. And to do this, we have defined f of gh to be the measure of sigma not to be a homomorphism. So it was what it was. I don't remember exactly what it was. So it was sigma of gh minus 1 power sigma of g sigma of h. And in this way we see that E is isomorphic to a group, to the group, let us call it A, G, F, yes, which is JF, which is G times A as a set and has multiplication defined by the equality G A multiplied by HB. We get on the first component GH, and on the second one we have f of GH plus AH plus B. Yes, we have shown that if we define f in such a way, then we will get exactly this structure. So first we want to describe all f such that this equality really defines a group, and then we want to understand what f give isomorphic extensions, what f give non-isomorphic extensions, like the extension is obvious. Yes, this map is projection of the first component, and this map is injection to the second one. So we have checked the associativity of the product. T0 has to be equal to G0, H0, T0, and this equality is equivalent to the fact that f of g h t plus f of g h times t is equal to f of h t plus f of g h t. And if we compare this and this, we will see that it is equivalent to the fact that f is a Tuka cycle in these terms, yes, as a map from g times g to a. So it is equivalent for f to belong to Z2 of GA. If we consider Z2 of GA as a subset of this home set. So we have not checked that if f satisfies this equality, then we really get group structure. Yes, this equality follows from some part of associativity, but you can check, like writing down everything and seeing that really if this equality is satisfied, then for any three elements associativity holds, and there is, of course, unit which is 1, 0, and each element has inverse 1. So to describe all extensions, it is enough to describe all cocycles, but it is in fact a big deal. But we are interested not in all extensions. We are interested in extensions modular isomorphism. Yes, and so the question is, what f define isomorphic extensions? So what data determines f? In fact, G and A are fixed. The G structure on A is fixed. So the only thing that we have chosen is the section sigma. Yes. And so if two elements f correspond to the same section sigma, if two elements f correspond to isomorphic extensions, then to different maps f, then in fact they correspond to different maps sigma. Yes. So if we have like f1 and f2, and they define isomorphic extension, this means that we can consider them as maps for the same tension but for different sigma. So how one sigma can differ from another sigma? Like sigma, what I recall, is a map from G to E such that beta sigma is IgG. So if we have some sigma tilde from G to E such that beta sigma tilde is IgG, yes, then in fact for any x, for any x, beta sigma of x is equal to x, yes, and it is equal to beta sigma tilde of x, which is equal to x2. Yes. And hence, sigma of x times sigma tilde of x inverse lies in the kernel of beta, which is A, yes. Let us denote it by by h of x, I think. Okay, let's denote by gamma of x. And then we get some map gamma from G to A. And for any map gamma from G to A, we can construct sigma tilde in this way, yes. Like sigma. Sorry. Let us write in this way, okay? Simply for convenience. So sigma tilde of x is equal to gamma of x sigma of x, yes. And for any set theoretical map gamma from G to A, we can define sigma tilde in this way, and we will get a section, of course, because A is exactly the kernel. So now let us compute our new cocycle f tilde. What is f tilde? F tilde of x is of xy is sigma tilde of xy minus 1 sigma tilde of x sigma tilde of y, yes. So let us here it is gamma of xy sigma of xy minus 1 times gamma of x sigma of x sorry. Sigma of x, gamma of y, sigma of y, yes. Well, probably it is not. Okay, sorry, let us write now very little. It's the same thing. Sigma of x minus 1, sigma tilde of x, to have the equality that this guy is equal to sigma of x, gamma of x. Then here will be sigma of xy, gamma of xy. Here sigma of x, gamma of x, and sigma of y, gamma of y, yes. So it is gamma of xy minus 1, sigma of xy minus 1, sigma of x, and here we can interchange them to have sigma of y, and here it will be sigma of y minus 1, gamma of x, sigma of y, which is by our definition is simply gamma of x times y. Yes, it is the definition of G-module structure on A. It acts by conjugation. So times y and gamma of y. Well, now like gamma of something lies in A, yes, and this guy is f of xy, and it lies in A2, yes. And since A is abelian, in fact, we can rewrite this as f of xy plus gamma of x y, gamma of y, let's start with that term, gamma of y minus gamma of xy plus gamma of x y. So we have replaced the multiplication by addition because as elements of E we multiply them, but it is the same as make the addition of elements of A, yes. Like in E we denote the operation by multiplication because there it is not abelian, it's not commutative. But since all these four guys lie in A, we can write the result as via some operation A. Yes. So f tilde of xy is f of xy plus something like this, which is, by our definition, is the same thing as here, yes? So it is f of xy plus delta y, delta gamma of xy. And so we get our theorem that says that any group extension A E G with a fixed G modular structure A is isomorphic to the extension A G A F G for some Tuka cycle F and two such extensions continues here. Two such extensions A G F G and A G A F tilde G are isomorphic if and only if F minus F tilde lies in B2. So if and only if F minus F tilde is a coboundary. And hence there is a canonical one-to-one correspondence between isomorphism classes of extensions A, E, G and H, 2, G, A. This correspondence simply takes some Tuka cycle representing an element here and put in correspondence this extension. This. In particular, for example, if you have two groups and like not two groups, you have a group G, an abelian group A with G modular structure, such that the second homology is 0, then any group extension of G by A splits, etc., is isomorphic to the extension corresponding to semi-direct product. And using this, we will prove a theorem that states the following. Let MQ be coprime numbers X, okay, let's be X be a group of order Q, G be a group of order M, then any extension X E G splits. Etc. If you have some group, you have found their subgroup X such that you have a finite group, you have found a subgroup X such that the factor group has order coprime with the order of X, then in fact your group is a semi-direct product of this subgroup and the factor group.
Previous theorem was stated for abelian groups?
Huh?
Previous theorem was stated for
yes.
abelian groups? And this,
It is like theorem. We will prove it.
Oh, okay.
So what we have proved is exactly the first step in the proof. The first step is to say that if X is abelian,
corollary?
Huh?
It's a proof of corollary.
Yes, yes. The theorem was proved before, was stated. If X is abelian, then the assertion follows from already proved facts. Since H2 of Gx is equal to 0. The previous proved, the already proved facts is this theorem and the fact that if you have a group G of order M, then M times Hn is 0, yes? Like we have proved that M times H2 of Gx is 0. Yes, obviously. Q times H2 of Gx is 0. Because the multiplication by Q simply multiply the result, and the result lies in X. Yes, where multiplication by Q is 0 because it's the order of X. And since M and Q are coprime, it follows that H2 of gx is 0. And then this theorem says that any extension of g by x splits. Well, it says that all extensions of g by x are isomorphic, and this means that they all are isomorphic to the extension corresponding to the semi-direct product. So in fact, only for this part we need our theory. Now we will make some group theoretical passage using Sylow theorems and related things. So let's first reformulate later what we want to prove. So we have an extension x e x e sorry e g such that the order of g is m, the order of x is q, and the common divisor of m and q, the greatest common divisor of m and q is 1. Then the extension splits if E contains a subgroup of order m. Yes, because in this case the subgroup doesn't intersect with x because m and q are coprime, and so it maps to G isomorphically. And we can simply take the inverse of this isomorphism. We have proved this for the case where x is abelian. So now we proceed by induction on the order of x, which is q, and m is fixed. So the base case is proved. First of all, the base case can be assumed to be x equals 1, but we have proved for x of prime order, we have proved for x of order p square. Let us now pick some prime p that divides q and denote by big P the Sylow Sylow subgroup some prime number that divides Q.
Oh, divides. Oh, okay. Yes.
Cell subgroup of X and of E simultaneously. Like since P divides Q and is coprime with M, then any Celo subgroup of X is a Celo subgroup of E, and any Celo subgroup of E lies in X and is a Celo subgroup of X. So the set of Celo subgroups of P Celo subgroups, the set of P Celo subgroups of X and E coincide. So what do we have? We have following diagram. We have E. Let us denote by N the normalizer of P in E, then N intersect with X is the normalizer of P in X, yes? Normalizer are elements that normalize P, such that conjugation by them induce some automorphism of P. So what else? So we also denote by C we denote the center of P. And since P is a P group, C is not 1. Yes. Now we have the following diagram. We have E, we have X, and the index of X in E is M. Here we have N. Here we have N intersect X. Here we have P, C, and unit group. Unit subgroup, yes. Now, the index of N in E is the number of P Celo subgroups of E. Yes. If you have if you have a CLU subgroup, you take its normalizer, and the index of normalizer in the group is the number of CLU subgroups, because all CLU subgroups are conjugated to the chosen one, and if you conjugate it by some element, then the result coincides if they lie in the same coset modular normalizer, and don't coincide if not. I don't remember what coset, right or left, but something like this. And analogously, the index of n intersect x in X is the number of p-CLU subgroups of X. Yes, because n intersect X is the normalizer of P in X. So these two numbers coincide. So these two numbers coincide too. And if you multiply this number, the index here, by m, it will be the same as you multiply the index here by this. Yes, and since here and here indices coincide, here indices m2. Yes. So now we have, n intersect X is a normal subgroup of n, yes, and P is a normal subgroup of n of n. And in particular, a normal subgroup of n intersect X. And hence we can consider the following extension. N intersect X factor P is a subgroup of n factor P, normal subgroup, and the factor is n factor n intersect X. Yes. And this guy is the order of this guy is m, and the order of this is something that divides Q but not divisible by P, etc. It is less than Q, and we can apply our induction statement, and we see that there exists some subgroup of n factor P would exist there exists some subgroup of n factor p of order m, yes, and let it be some h factor p for h between p and n, yes. So we have here subgroup H that contains P such that the index is M. Now let us consider the extension P factor C H factor C so C is the center of P, so C is normal in P. It is not the center of H, but since H acts on P by conjugations, it has to, the conjugation has to preserve the center, so C is normal in H. So we can write this guy, yes. Since conjugation by elements of n that contains H preserve the center of P, since it's automorphism. So the factor group is H factor P. It again has order M. Yes. And now the order of this is less than Q again, because the order of P is less or equal than Q, and C is not unit because it is the center of P group. And hence we can apply our induction hypothesis and get some subgroup L hence there exists subgroup L that contains C and is contained in H such that the order of L factor C is M. And finally, we have the extension we have the extension C L factor C. Here the order is m, and here we have an abelian group. So there exists subgroup K L of order m. And we are done. Because K is a subgroup of L, L is a subgroup of H, and so on. K is a subgroup of E. So it is some application of homological algebra, what we have studied. So now let us consider a modular equation. Now consider the extensions. X E G of G by X, where X doesn't have to be abelian. What can we do in this case? First of all, let us understand what structure such an extension induces. Before, when X was abelian, we had G-modular structure of G-modular structure on X. But now it cannot be, because modulus by definition abelian group, first of all. And secondly, when X was abelian, we had a homomorphism. X was abelian. We had a homomorphism from G to the group of automorphism of X. But now we don't have, because if we take some X, yes, and consider the, we still have the homomorphism from E to the automorphism group of X, because X is a normal subgroup of E, and so like E from E goes to the conjugation by E well, probably I'm a little wrong, because in fact if we need to put here op. So nu e of x is e minus 1 xe, yes, for x in x, e in e. No, e is not a very good letter. Let it be y. Because we sometimes unit. Yes, and since x is normal, we have really a homomorphism from e to out x op. So, but if y is in fact in x, then we need not have nu y equals to id. Yes. Before, when x was abelian, we had this because conjugation by an element of abelian group is identity. And because of this, like x was in the kernel of this map, and we could this map induced a homomorphism from G to the automorphism group of x. So we have e, yes, goes to out of x. Yes, and we have x here, yes. Sorry. To here. But such elements, elements nu y for y in x, yes, lie in the group of inner automorphism of x. Simply by definition. And hence, the homomorphism from E to out of X induce a homomorphism from G to out of X. I don't know if what's the difference in pronunciation. Induce a homomorphism from E factor X, which is G, to out of X factor in of X, which is the group of outer automorphism of X. So we have some homomorphism from G to the group of outer automorphisms. Like a reminder, that there exists an exact sequence of groups. So there are automorphisms of X, like there is a subgroup of inner automorphism, yes, and it is the image of the map from X to out of X that sends X to the conjugation by X, and it is a normal subgroup, so the factor group is group of outer automorphisms of X. And here the kernel is what? What elements of X induce the center is the center of X. So we have shown that any extension X E G induces a group homomorphism psi from G to the group of outer automorphisms of X. And the problem that we will consider now is the following. The problem is to describe all extensions of G by X that induce the given homomorphism psi from G to out of X. So now data that is given is G, X, and psi. The difference is that now it's not obvious if for any G, X, and psi such an extension exists, and we will see that in fact it does not always exist. Well, so let us follow the same algorithm as before. Let us pick some. Suppose that we have an extension And now we first will deduce what's the middle group. We have an extension. X alpha E beta G. What's the middle group? Let us pick again some sigma. Yes. Let us pick sigma from G to E such that beta sigma is the identity on G. So sigma is a set map. Map of sets. Well, again, if sigma will be a homomorphism, then the extension splits and so on. Or not? Yes. But in the opposite case, it doesn't split. Well, now let us define as before. Let us set as before. F of gh to be sigma of gh minus 1 sigma of g sigma of h. So it's the abstraction for sigma to be a homomorphism. As before E is as a set simply the direct product of G and X, yes. But now we need now F doesn't define the structure because we don't know how G X on X, yes. So we also need the data gamma X from X to X. Gamma X is an element of automorphism group of X. Yes, and it is defined by the equality gamma X of y. Gamma y of X is sigma y minus 1 X sigma of y for y from G and X from X. Yes. So gamma y is the conjugation by sigma of y. But gamma, of course, is not homomorphism. But we have, of course, the class of gamma y is psi of y. It is the class of gamma y in out of X. now we also need to have a measure of how gamma differs from homomorphism. So wait a minute. So let us calculate gamma y, gamma x, yes, gamma z of x, yes. It is what it is. First we apply gamma z, yes, y of sigma of z minus 1 x sigma of z, and then it is sigma of z sigma of y minus 1 x sigma of z sigma of y, and we know that this guy is sigma of zy, yes, f of zy by this formula. So it is what? It is gamma zy of x, and we also apply the conjugation by f of zy, nu zy, and nu f of zy.
What is the last, after the last equal sign, what is it? It's gamma f, no.
Here, nu f of zy, gamma zy. Here is the reason why I put up there, because here gamma y, gamma z, and here gamma zy. Well, so now we can write the formula for multiplication, yes. GA, GB, HB is what? Yeah, well, J corresponds to, of course, to sigma of G times A, yes, where G is from G, A is from X. So if we multiply them, we will get, as before, GH, f of GH times gamma H of A times B. Well, so as before, we can check that the associativity law applied to the elements G1, H1, T1 implies like the same thing as before, but now the order is important. Yes, implies that f of xy gh t times gamma t f of gh is equal to f of ght times f of ht. The calculation is the same. You first calculate the product of these two guys, then multiply by T1, and then you first multiply this and then multiply by G1, and you will get exactly this equality as the equality required for associativity. So, we have defined the multiplication, yes, that depends on some f and some gamma, yes, and we have shown that this gamma and f have to satisfy this equality, that be equality 2, and the equality 1, which is this one. So gamma y, gamma z is equal to nu f of zy, gamma zy, yes. I don't remember, I have introduced what is nu something, yes? Not? Yes. Where, of course, as before, f of gh lies in the kernel of the map beta, yes, so it is an element of x. But now it is not, of course, cocycle, because here we have multiplication, because x is not an abelian group. So the same theory we can't apply. We need something else. So yes, it is the equality 2, and this one is equality 1. And let this one be star. So what we have proved is the following theorem. Any extension x EG with that induces a given psi from G to out of X is isomorphic to the extension X G X gamma F G, where G X for some gamma from G to out of X such that the composition G gamma out of X, and here the canonical projection to out of X is equal to psi sum F from G times G to X that satisfy the equalities one and two. Yes. Where G X gamma F is G times X as a set and has multiplication defined by star. Yes. This is what we have proved. And as before, this map is this, and this map are simply projection of the first component and inclusion of the second component that correspond to this presentation as a set. And this is what we have proved, but converse is true if gamma from G to out of X such that gamma and then projection is psi and F from G times G to X satisfy equalities 1 and 2, then G X gamma F is a group. That, of course, which is an extension of G by X inducing psi. So if we have constructed such gamma from G to out of X and F from G times G to X, that the class of gamma is psi, and that gamma and F satisfy equalities 1 and 2, then we get an extension of G by X that induces the required psi. And if we have an extension, then such gamma and F can be constructed. But now the question is for which psi, for which G, X, and psi, such gamma and F can be constructed. Gamma, of course, can be constructed simply as a lift of psi, yes, because here we have an epimorphism, and we can make the synthetic section. But how to define F is not clear.